case. So one parameter unipotent groups basically come. You can take a morphism of a bigger group. So you have a morphism of a bigger group from SL2 QP or R, a morphism from that to the same, to the P part of my group G. And then my one parameter unipotent group is going to be equal the image of the unipotent group in the SL2. And the advantage of this is that now I have also a friend, this image of this matrix. So now T is inside the multiplicative. So now this is, if you want, T to AT is a morphism between the multiplicative group to my group G, maybe G. Anyway, and the important thing about these two things, of course, is that if you look at AT US, AT inverse, this is going to be UT squared S, the way I wrote it. Okay.
Ron, what's the value of capital T? Anything?
As T goes to infinity. Something needs to go to infinity. Thanks. The ball becomes louder. What the ball means, sort of, that the ball becomes louder. Now,
what are you explaining on the last one? What is this? This is an example?
No, I'm sort of saying that I define to you one parameter groups, maybe in a slightly, I don't know, slightly, maybe intimidated by Alex trying to talk a bit more algebraic than I should, but never mind. And I'm saying that in fact, these one parameter unipotent groups come from an SL2. I'm basically saying, I should have said, and I want to say, this is Jacobson-Morozov in disguise, or not so much disguise. This is Jacobson-Morozov. Jacobson-Morozov is about Lie algebras, but so it's not true for Lie groups the way I wrote it, but we are talking about algebraic groups. What I wrote is literally true, I hope. Okay, and now there's a theorem. So this is Ratner's theorem. There's another important theorem that Ratner's theorem is a major ingredient in. This is a theorem of Nimi Shah. I think in the S-arithmetic context it's probably due to Gorodnik and all, though maybe Tomanov also work is also relevant, but I think this is Gorodnik and all. And it says the following, it says it's sort of something very similar under the same situations. So f is again bounded, continuous on x. I'm now taking a unit ball. Maybe I'll use my notations I'm used to. I'm taking a unit ball inside my unipotent. I'm averaging over this unit ball. But I'm also applying this element, this diagonal element in front. And okay, I'm normalizing everything to have volume 1, and this converges to the average. It sort of looks quite similar on some periodic orbits L, but L now, Lx0 periodic, and of course I need to say as absolute value of t goes to infinity. Something needs to go to infinity. Lx0 is periodic, and L, sort of the nice thing here, it contains the full image of phi, and it's contained in G. And now I could write this if I wanted, and I won't. So think I can write it as s less than or equal to t squared f of us atx ds. Okay, so somehow it's very close to Ratner's theorem. Ratner's theorem, I fix a point and take longer and longer orbits. And here I'm doing two things at once. I'm changing the base point and taking longer and longer orbits. Okay, now if you change two things at once, usually things become more complicated. It's sort of, you change one thing at a time. That's sort of what you know, any kind of debug, whatever. You change one thing at a time. But here, changing two things at once actually simplifies life considerably, because the possible exceptions here are much less. And one way for me to think why this is true, so why is sort of this changing two things at once better behaved than changing, than just taking a one parameter group, is that there's a random walk interpretation. So take mu L, the measure on G, so this is a probability measure on G.
Can you repeat why L is different here?
Hmm?
Can you repeat why L is different here?
Because magically here, so somehow you're taking average of big unipotent orbits, so somehow you'd expect whatever you have would contain L, would contain this big unipotent orbit. But here magically, it has also two more directions that you don't, didn't expect a priori. And these two extra dimensions basically limits, so the possible candidates for L are much fewer. So in many situations, for instance, here you might have many obstacles, and the obstacles come in complicated family, and here maybe you have less obstacles, or the obstacles just come in discrete things, not complicated families. So if I take mu L, this is a probability measure of G, to be this average of delta at A, L, U, S, ds, S less than or equal to 1, okay, this is a probability measure on G. And I would try to see what happens. So I'm taking I'm taking some point. I'm looking at the measures. I'm taking some point x0 in my space. I'm looking at the random walk after I apply n times to this point. Okay, and then I can integrate f after f of maybe f of xc d xc on x, right? I have a probability measure. This is a probability measure on G, but this is a probability measure on my space because I multiply it on the point. And I take the average of f. This is exactly the integral over. This is exactly the integral over of f of a applied L to the n times us x0 s less than or equal to 1. This is exactly true if P is a prime, if we work over QP, or almost true, exactly, and almost true up to some e to the minus L infinity norm of f if I'm working over R. So periodics are a bit nicer and simpler. But even in the real case, you basically have these kind of averages that Nimish studied are basically random walks. And random walks somehow, okay. There are probably some probabilicists in the crowd. At least it makes the probabilicists happy. Okay, so now I'll tell you what is. So I want to say a lot of things, and one thing I'm not going to say so much is survey, historical survey, which is a problem because many people contributed to what I'm going to say, etc. But I'll just tell you the theorem that I want to talk about today, and after that maybe, so it's a theorem by Amir Mohammadi, by Lei Yang, and myself, and okay, there's also some 90% finished draft on overleaf. So I'm taking G to be a Q group. That is a form of, so that if I plug in the complex numbers, I'm going to get SL2C to some power. I'm not assuming the group is Q simple or something. I'm just assuming this. So maybe, so a good example would be G just to be SL2 times SL2 over the rationals. Another, and S a finite set of places. But the important thing is that N is not bounded and sort of the what form. So basically, a form of SL2 comes from. So this is going to be a product. So G is going to be a product of forms of SL2. Each one is going to be a division algebra, a quaternion algebra, or an SL2 over some field. And so I'm not in the field. I'm looking at a set of places. And then I'm taking, of course, G to be G, Q, S. So quite possibly one of the components of G could be the group over a degree 13 extension of QP. That sort of certainly could be one of the things here. Gamma is the integer points, or finite index subgroup of the integer points, or a congruence lattice. And you could use, anyway. And phi, like we said, is SL2 QP into the QP part, or maybe SL2R. And then we have US, T as before, and then what I'm going to say, this is actually quite convenient for smooth F. Smooth compactly supported F. If I compare, so one of the following things happen, or let's say this way. For every point x0 in X, no exceptions whatsoever. If R is bigger than 1 over the injectivity radius at x0 to some power, and maybe T is bigger than some power, T is bigger than R to the C, one of the following happens. So one of them is that you have equidistribution for this orbit. So this is less than some R to the minus gamma times maybe the Sobolev norm of F, some kind of Sobolev norm of F, some moderate, basically. I mean, it's a bit messy because you sort of need to explain, but some measure of how wildly F varies and how big it is for all smooth F.
Depends on what. Yeah, little gamma.
It's basically the spectral gap hidden. But this is T and this is R, so and second thing is that x0 is near some, so there's some g1 there is g1 in G, and the Q subgroup, semi-simple. Also, it would also be a form of SL2 to the maybe other form of SL2 n prime, such that G1, the point corresponding to G1 in the quotient, is very close to my original point, t to the minus, I don't know, 1 or something, r to the c. So I'm thinking t as being much bigger than r, so this is a very tiny thing. Is the height of h, it's sort of some, you could, Q objects, you could define height on them, which would be essentially, most reasonable people will agree what it means up to polynomials. Such that basically this is basically the effective analog of saying that I am on a periodic orbit, such that phi of this SL2 is contained, or maybe I put it G1 inverse is contained in H of the point. Right, so basically H QS to a Q subgroup that corresponds to a closed subspace of G mod gamma, and then this is going to be a periodic orbit of some group, and so this is exactly what we were discussing. So this is the theorem, and
Is height really algebraic or anything, or?
yeah, I mean basically the Lie algebra of H is going to be a Q subgroup of the Lie algebra of G, and you look at the height of that.
Is there some checkable condition to make sure the second case does not happen?
Often it is.
So the thing that on G there is no height bound, there is no height.
So, okay, I mean, there's various implicit constants. The height of G would be included in these implicit constants. But everything here is effective, so nothing really, so, I mean, I don't know, there should be some kind of polynomial in the height of G. I don't think there's anything sort of super frightening. There's basically the height of G, the spectral gap, which, okay, spectral gap in this context is just a number. I mean, it's not, in this case, the world record is by Peter and Kim, yeah. Anyway. Now, it's, so the special case of SL2R times SL2R, SL2C is by Mohammadi, Zhiren Wang, and myself. This is Zhiren Wang. I'll write it on the part of the board that actual people maybe can see. And so the important thing for us was to allow now many factors, that sort of in number theoretic applications, that's actually something which occurs, having many factors. So, for instance, this is not something I completely understand. but one of the applications of Ratner's theorem in this exact context was by Cornu and Watzel showing non-vanishing of L functions. And so the first paper by Watzel, which had two SL2s, and there was a second paper by Cornu and Watzel, presumably proving that more L functions don't vanish using many SL2s. So, there's also other, like I said, there's also other important prior works or other prior work. So prior work, and let's just to, of course, there's the whole 2,000 years of mathematics, but in the semi-simple case, non-orospheric, whatever that means, I think some works are by Margulis and myself, by Lei Yang, by Mohammadi, Zhiren, Lei Yang, and myself. And I think one of the reasons I wanted to write this list of names is that I'd have an excuse before I run out of time to mention an important work by Wei Kun He and Timothy Bernard, who have some quite beautiful quantitative equidistribution results, not for Ratner's theorem, but for random walks. But as we said, random walks in some sense is a more, okay, random walks is somehow very closely related to what we're doing here. Now, so we are very proud that now we can do things like, so to begin with, like a product of SL2 QP, big product of 14 terms, or maybe an SL2 of a degree 14 extension of QP, etc. But let's just look at the simplest case. Okay, we think it's almost a trivial case. I'm just taking SL2R modulo SL2Z times SL2R modulo SL2Z, and of course I'm taking this one parameter group. Okay, this is the simplest case. This was sort of like we said in this paper with Amir and Zhiren. But I want to convince you that, I mean, when you write an abstract theorem on a board, you sort of don't really get any kind of feeling if it has any kind of content or not. So I want to sort of take the simplest case and write an application that I think is nice. So you take a torus. Okay, this is just a two-dimensional torus. And you look at the eigenfunctions of the Laplacian on this torus. So of course we know it basically comes from the size of the elements in the dual lattice. It's 4 pi squared v in the dual lattice. That's sort of the eigenvalues. Let's call this E of y. One slightly annoying point is that in this case, because of symmetry, everything has trivial multiplicity too. So basically, I'm just I'm not counting this trivial multiplicity too. So for me, the number of lambdas inside the eigenvalues which are less than t, doesn't go according to Weyl law. This is what Weyl law gives, and it's just, okay, in this case it's just area of a circle or something. But for me, I'm sort of, because I'm just compensating for trivial multiplicity 2, it's going to be 1 over 8 pi. And whatever this constant is, I'll just call it C. Now, if you have a big n by n Hermitian matrix, the eigenvalues tend to repel themselves. They don't want to be close. If you have, but here this is, whatever these numbers are, they are not eigenvalues of any random anything. So the reasonable assumption is unless something special happens, it's reasonable to assume that you basically that this set of numbers will behave like Poisson random variable, basically Poisson in each. So you know roughly how many they are, and each one is basically completely random. They don't know about each other's eigenvalues. So this is an instance of the, so typically expected, whatever typically mean in this kind of literature. They behave like, should behave, these set of numbers should behave like Poisson random variables with this intensity C.
This is the theorem or this is the concept?
Well, it's a statement with obvious counterexamples, which is supposed to be true in some sense. Physics, yeah.
You need to pick the right definition.
No, I mean basically when this doesn't, I think maybe when it doesn't happen, you should be able to say something interesting about the system. That's how I would interpret it. If this doesn't happen, this is an interesting thing to note.
It's not clear, it's not an empty setting.
Yeah, so, okay, I mean, probability is complicated. Let's try so if I want to test it, I don't want to talk about complicated thing. Let's just talk about pair correlation. That's one way to try to test it. So what will be pair correlation? So I'm looking at just a number. So I'm looking at the number. I'm looking at the eigenvalues. Lambda and lambda prime less than t, of course, inside the set of eigenvalues. Lambda minus lambda prime is inside some interval alpha beta, and I want to know how many of these are. Now, basically, if I assume that these eigenvalues don't know about each other, I said that I have about ct many choices of lambda, and then the number of lambda prime I can expect between lambda plus alpha and lambda plus beta should roughly be the intensity of the Poisson process times beta minus alpha. So this is what you would expect. If it's Poissonian, this is what you would expect. And maybe sometimes instead of looking at the dual lattice, maybe it's sometimes instead of taking the dual lattice and the norm, sometimes it's convenient to look at it. This is just a two-dimensional additive space. You could look at it as a fixed lattice and a varying quadratic form. I'm sort of going to use these two points of view very non-pedagogically, whichever one is at the moment better is what I'm going to use. So it's obviously sometimes false, right? If Q is integral, I'm taking an integral quadratic form, I'm looking at it at the integer values, I'm going to get integers. I'm not going to get many pairs which are going to be of distance between 1/4 and 3/4 apart. That's not going to happen too much. It's obviously false. And actually it's false even in the worst case. Also it's false in two ways. Too few pairs if let's say alpha is 1/4, beta is 3/4, and I can get too many pairs for instance, e.g. Too many pairs. So for instance, if I'm looking at x squared plus y squared, the number of lambda prime up to size t, for which lambda is actually equal to lambda prime. So the number, I'm sort of ignoring trivial multiplicities, but I don't want to ignore non-trivial multiplicities. This would be something like t log t, so it's sort of just way off. And then again, Peter showed that somehow for dense d delta set of tori, this thing is, because you have this thing is off, you sort of get the wrong asymptotics, fails to be Poisson. To have right asymptotics. But for almost every y, it's true. Which, okay, is quite possibly a satisfying answer physically, or maybe. But so like I said, what I want to say is that Berry-Tabor holds, or you could say a story. So a theorem like that was proved actually by Eskin, Margulis, and Shachar. So what did they prove? If my quadratic form is not extremely well approximable by an integral form, the watch, as usual, becomes more and more frightening as you go along the talk. So I'm not going to tell you what it is, but you sort of some kind of Liouvillean behavior, okay? Sort of a strong pathologically approximated by integral forms. Then Ry alpha beta t does indeed behave, and you need to make another assumption. 0 is not inside my interval. Then you have the right asymptotics.
Big integral is not the same. Big integral, something healthy.
When I can prove using dynamics something about the integers, there's nobody that's happier than me. Okay, when I can prove something about the integers using dynamics, that's for me the definition of bliss. But okay, but sometimes you talk about non-integral things. But this is what I said, right? Berry-Tabor, so the sort of physics conjecture is you have Poissonian behavior unless you could say a nice story, why not? And this is exactly a nice story, why not? And so it turns out, and I'll try to explain in a couple of words why, that the SL2R times mod SL2Z squared version of the effective statement actually gives something. Effective statement says the following, gives the following theorem. This is maybe not the best pen that I have at my disposal. And this is a theorem of Amir, Zhiren Wang, and myself. If Q is not with some explicit parameters, you could choose them, but the other implicit parameters would depend on these explicit parameters. If your pair correlation does not have power saving, okay, you don't have some kind of power saving in the pair correlation, there is an explanation for that. And the explanation is unique, two unique up to sign vectors v1, v2 inside my dual lattice. The size is small, and the inner products are basically orthogonal. And the point is, there was a reason why Shachar and friends excluded 0 being in the interval. So if you had a rectangular torus, if you have a rectangular torus, and everything appears not in multiplicity 2, but multiplicity 4. So you just have too many things. And this is not quite saying that you are rectangular, but it's also you are rectangularish. So if you're rectangularish, you need to add some kind of correction term. An explicit correction term needed in that case. In that case, and why are these things related? And I should say also that so Eskin Margulis Moses actually handled not just a difference between values of two binary quadratic form, but the general quadratic form of signature 2-2. That's sort of more general than what we handled, but I should say that the EMM result was effectivized in full by Jules Linden, very nice work using. Okay, just to mention all of the nice things that were done. But why is this related? So basically, so if I have two vectors, the difference between their size is the inner product between the sum and the difference, which, if I wanted to, I can think about the determinant of v1 plus v2, and then v1 minus v2 rotated by 90 degrees. So now, up to index 2 issues on which I'm going to lie. If I'm taking two vectors in a lattice, the sum and the product are two other random vectors in the lattice. So I'm basically looking at, so basically I can work, instead of working, I'm looking at the values of the determinant of v and w, where v is inside some lattice, and w is inside the lattice rotated. And I mean, when I apply any 2 by 2 matrix of determinant 1 on both vectors, I'm not changing determinants. So it turns out that any two vectors here, morally at least, morally, if V, W are roughly of size T, when I can find some I could sort of maneuver them by taking the U S up to size 1 maybe, and then T is basically something like log T, orbit of V and W. Basically, you could read from it pretty easily whether this determinant is between values alpha and beta or not. So that's somehow how group actions come into this counting question. Yeah, so as usual, I worked hard to try to say something meaningful about the proof in the last 10 minutes of the talk. I'm not sure if I have, actually probably I have a few more minutes, right? I actually started late, so how many minutes do you give me?
5.
So let me say something about the proof. It's not quite so. I've mentioned several. So this is a effective equidistribution in important flows. It's something that I've sort of worked on with co-authors in the last few years, and we have different approaches and sort of we approach it from many different directions. This proof somehow goes in a different direction. In particular, it doesn't really go literally in the usual Bourgain-Gambourg strategy. It's not quite. So what we do, so one way to think about it, so I'm looking at, so maybe let's say mu t is as before, right? It's sort of the integral delta a t u s s decimal to 1, this is the probability. And you take maybe ut times some delta x0. And suppose, and one of the things, and suppose this has dimension d at scales between delta and 1. And basically delta would be, okay, suppose I can establish this somehow. And what does dimension d at scale delta mean? In particular means that if I'm taking most of the space can be covered by delta balls, which have measure at most delta to the d. That's how effective dimension. Now, and this kind of dimension, this doesn't change. I can apply here US, this doesn't change. Delta balls are basically going to be delta balls. Now, our Lie group of G, you basically write it as G plus. If you conjugate, if you apply add AT on this Lie of G, there's part which is expanded, including my Lie algebra of my unipotent, part which is left B, and part which is contracted. Now, and this part is sort of has, it was influenced by part inference part also we worked independently in similar directions, but sort of very close to what. But this part now of the argument has direct relationship to the work of Hay and Bernard. We show that for most S, US mu t delta x0 of something which is of size delta in the plus part, delta half in the 0 part, and I don't really care how anything about it's sort of full size in the minus part. We show that this has so somehow if you would think that everything behaved like if all of these things were independent, this is what you'd expect, but you have some kind of gain. You get some kind of gain of dimension. Then you apply a t for t something like I think t delta to the minus 1/2, minus 1/4, sorry. So after you apply this AT, the way it's transformed, AT takes this kind of balls into delta half balls. So you get better dimension for more restricted scales. And this is true unless something special happens. And the key innovation in our paper is sort of elucidating what something special happens, making this something special happens from a local something special happens to some kind of global something special happens, and then using, and in this sense what we do is closer to what Margulis and Tomanov did than what Ratner did. Ratner basically took an orbit, allowed it to do whatever it wanted, and then it handled the consequences. Tomanov and Margulis basically took an orbit, so already at the beginning they sort of make sure to ensure that this orbit is not going to behave in bad ways that they understand, and then they prove that it behaves well. So basically this something special happens would contradict things we know before we run the algorithm about how our orbit will behave. It's kind of using linearization. And then once you have big dimensions, then this is quite close to what Manuel said. You have quasi-randomness, you have this Vinkatesh trick, you sort of finish off one way or another. Okay, thank you. There is, so, okay. So how do you pass, so there is a projection theorem. How do you pass, this is in some sense a projection theorem, but it's sort of, but you sort of combine, you combine a projection from G to, or let's say, Lie algebra of G to G's, and you combine a projection just to G plus. So there are sort of two projection theorems are combined together here. And we don't use, interestingly, we don't use the Bourgain sum product thing. We use something simpler. What we use is the following, the combinatorial statement that we use is the following. So I have here lemma position. So I have here pi t from R to the 3n to R to the n, which takes basically three vectors, 2 x plus dy plus t squared over 2z. Okay, that's a family of maps. And we have here a set S inside R 3 to the n. And it's sort of, let's say, delta separated. And, okay, maybe some other small assumptions, but basically S is something like delta to the minus alpha. And then the covering number, delta of pi t of S for most t is at least delta to the minus alpha over 3 and plus again, unless S is essentially essentially comes from a convex set in Rn. So basically, if you take a convex set in Rn and you take x, y, and z inside this convex set, you're not going to increase anything. And unless you are in this situation, in this projection, you gain something. So that's the exact projection theorem. That's sort of what we use, which is simpler, strictly simpler than Bourgain's projection theorem, but that is sort of the place where we gain dimension is this projection theorem. Yeah.
You set it up generally at the beginning. This argument is special to SL2 forms.
So
In other words, you have some other theorems which do use projection theory. So what sort of the status of
the status is that we're working. So, like I said, basically, so I have here an SL2, and I have here the Lie algebra of G, and I can write the Lie algebra of D as a sum of irreducible representations for SL2. And in this case, we have the nice situation that all of the Wi's are the same representation. That helps us. And we can handle the case, we can also handle the case where we have basically SL2 plus, and then other representation which are of the same size. But we, at the moment, it's not, it's not, there are some difficulties that you don't know how to overcome that frighten you, and there are some difficulties that you don't know how to overcome that you sort of feel that they are doable. So it's not that, but that's sort of the difficulty right now.